Hey everyone, hope everyone is doing great. Recently, Google has launched their Gemini File Search API. This could be an answer to the complex RAG architectures which we are currently having. So they built an File Search API which could able to understand your files and could able to retrieve answers from the files itself. So this kind of architecture we usually see in the retrieval argument generations. You're going to provide your own data to the retrieval argument generator and it's going to understand those documents. It's going to go through certain steps, making the document into vector embeddings and storing that in a vector databases and retrieving answer from them. So this was the basic architecture that we are having currently. So when I mention the architectures of the RAG systems, we do have them in a different phases, but Gemini has implemented all those things with a single API. So today we are going to understand how they build their single API architectures. So let's get started. We'll understand the architecture, the differences, and as well as the idea we are having on the analysis of Google's Gemini File Search API. So we could simply say that we are moving the industry away from the complex architectures that we need to implement. So we are having a huge architecture. So you could see here. So this could be the real architecture of rack systems. So if you want to build a rack system from scratch, so these are the steps we usually follow in order to build a sophisticated rack systems. Building something from scratch could be even more developer oriented, but Google has made it even more simple. So today we'll see what the Google Gemini File Search API is going to helpful in our use cases. So as you could see here, RAG defines retrieval, augmentation and generations. So we are going to retrieve the data that is being stored in a vector databases or that is being stored in any other format, and we are going to generate the responses by the questions that we are asking. The traditional RAG systems are monolithic tools, so they are having an architecture was step by step. So these architectures are rather composite, so they are more complex to understand for a naive person. So the different layers present in the original RAG architectures must be selected individually and they need to be configured individually. So the standard RAG architecture typically comprises of 5 stages. So when I mention the 5 stages, you could see those 5 stages here. So initial stage could be considered as a data ingestion. Whatever data you have, that could be either format of PDF, that could be either tables or a CSV file, that could be either images. So these are different type of data generally people uses in their use cases. So we are going to take this entire data a particular person is having and we are going to inject this data. We are going to convert this data into mission understandable language. As you probably know, the missions aren't been able to understand the natural language processing, so they aren't well versed with the NLP. So we need to convert that so that they could even understand our language. So we are going to inject the data using the data ingestion techniques. So we are having different data ingestion techniques. So for example, if we are having a simple text, if you have a PDF, we'll be having a simple text. So in that, we could even use that PyPDF. Using a PyPDF, you could simply extract all the text that is present inside that PDF. So consider other scenario. What if the PDF that you are giving have some tables, have some images? So this is where the architecture could be become more complex. So when we are extracting a simple text, LLMs are capable enough to understand what does the image can be converted into or what does a table can be do. But coming to the RAG systems, that's where the difference comes in. So you need to understand what type of tools that we need to use to convert the data that we are having, either that could be in table format or that could be in a PDF format or images into the ingestion format. So for that, I have given you a simple use case. Generally, if you have something kind of extraction, simple text extraction, we could go with the PyPDF or PyMUPDF. So when you go to the architecture of the PyPDF, you could see. So this is their GitHub repository. So it's a free open source Python PDF library capable of splitting and merging the text. So it could be capable of understanding and splitting those given input data into different things. So you can simply install PyPDF using this pip install PyPDF. So when your use case turns around simple text extraction, PyPDF could give you the best answer. So when you have some images inside the PDF, probably some PDFs could be having some images or kind of a graphical representation, right? So when the graphical representation comes into the picture, you could use the Tesseract or Easy OCR. extract all the features that are present inside the PDF. That could be an image or that could be a table using optical character recognition. So it's going to help you to inject the data if it's present in a format of images. The PDF contains all the three things. So it contains text, always it contains images, and also it contains the tables. So when this picture comes into the idea, we generally use Docklink or Camelot. So you could use any of those tools which I have given here, so that it could be useful for you, and all the links which are required for these things are mentioned in the description. You could go ahead straight away and use those things, and code files will be given at the last, so we'll go through all the things. So data ingestion, that could be even more simple. So I've given a simple example here. How does the data ingestion goes into? So we'll be having one PDF, and we are using this PyPDF to read the PDF. So we are defining a variable, and we are assigning it to the PDF reader, and I'm giving an example PDF. So it's going to go through all the pages and it's going to extract the content. And when extracted, it's going to give me what was the thing which was extracted by using a PyPDF. After extraction, so here comes the next process of after extraction. So we have our data and we have injected our data, and now we need to understand, we need to make the model to understand what we are giving, what we have made in the previous step. So here where the chunking comes into the picture, you're having a PDF of 20 pages. So at a time, model cannot understand all the 20 pages at a single point of time. So you need to have some chunking process so that the PDF could be split into different parts, and these different parts will be passed on, and that could be having more rich context. Say for example, in the 20 pages, page number 18 has more context than page number 1. So each page need to be understood by the model. So we'd be having an idea of chunking to make this process easy. So in the chunking, there are different processes we'll be having. We are having fixed site chunking, semantic chunking, which could be mostly useful for the NLP process we are using, recursive chunking, and the structure based as well as LLM. Let's say I've defined the size of chunk as 2. So we are having an example here. The quick brown fox jumps over the lazy dog. So this was a simple example that we are going on with. When I say that size of chunk is 2, so this entire sentence which I have provided is going to be split into the size of word 2. So you could see the quick have been compiled into one thing, quick brown has been compiled into one thing, brown fox. So you could see we are having some overlap in between those words, so that the context between these two words are maintained. So this is the idea of fixed size chunking. And now we will be moving on to semantic chunking. Yeah, in semantic chunking, we'll be having the meaning of the sentence. Let's say for example, the cat is sleeping on the sofa, the dog is lying on the couch. So I'm having 3 sentences here. Out of these 3 sentences, 2 sentences are being the same meaning. So you could understand what the meaning of the 2 sentences. As a humans, we are able to understand. And then when you come to the third sentences, you could see, right, the stock market fell sharply today. So this is a different sentence when compared to both of the sentences above, right? I mean, when I do the semantic chunking on the text that was been given by the data ingestion part, the top 2 chunks into one chunk. So it's going to maintain the semantic understanding between those 2 chunks, and it's going to keep that entire 2 sentences we are having in a single chunk. So this is the idea of semantic chunking. And properly, we are having some recursive chunking. Consider 20 pages PDF. So you're going to split that accordingly based on the recursive thing. Say for example, you're having 2 paragraphs at a single point of time. You're going to split the 2 paragraphs one by one. See, here could be a simple example of recursive chunking. You're having a sentence, you're going to overlap, you're going to maintain that overlap so that the context between these sentences are analyzed more easily. Yeah, and then we have LLM based chunking. So we'll be integrating the large language model into the picture here, so it could be able to understand what we are explaining. So they are capable enough to make chunkings. And we do have structured chunking, where we'll be using most probably we'll be using them in the financial things, or if we have some structure that was given by some company. Say for example, if we are having some Aadhaar card data, so that Aadhaar card data could be structured as we are having some image, we are having some addresses, name beside. So this is a structured document. So when you have certain types of structured document, this could be more helpful thing. So once this chunking has been done, you will be getting some of the chunks from the ingestion data that you have provided. So you need to convert the chunks into the embeddings. So this is the most crucial part where the data which you have provided need to be understood by the model. So we are making the data that could be understood by the model in the embeddings format. So we are going to convert the chunk data into vector embeddings which could be understood by the models. When I mention embeddings, so this is the simple example that you could see. So if I'm having a 3 sentences which could be written as 3 objects here, so these has been passed on to the embedding model. So these embedding models could be kind of anything. We do have Gemini embedding models, we do have OpenAI embedding models. So there are different vendors which are providing the embedding models, and the usage of which model to go with is purely based on the use case that we are having. So currently the embedding model we are going through the Gemini File Search API is a Gemini embedding 001, which will be seeing on to the further lecture. So when you pass an input to the embedding model, it's going to convert that into a vector which could be an understandable format by the neural network architecture. So the every input that we are having, the every chunk we have provided, if you are using a structural chunking, the chunks could be different. If you are using a recursive chunking, obviously the output could be different. So based on the input that the chunking we are using, you are going to pass it on to the embedding models. Which one to choose? So there could be an use case around which chunking should be we use. So I would suggest when you have the content well organized, so you have an organized content, so which I mentioned previously, Aadhaar card example, you could go with the structured based chunking. Or if you have some narrative topics, if you have some kind of poems that you're having, or if you want to make the chunk have an idea of entire base chunk, if you have an abstract which could be explaining all the things that are present inside all the document of a research paper, so I would suggest you to go with the semantic chunking. And LLM based chunking for unstructured data that we are having, so we are not sure whether the data is being processed or data hasn't been processed, so you could go directly with the LLM based chunking. And recursive chunking, so this could be the balance between the size and the context. So when you have a huge size and the context really matters for you, so I would suggest you to go for recursive chunking. So when I say the embedding models, we do have some sentences here. Let's consider the sentence, a dog is walking past a field, right? And we do have other sentence like look at my little cat, and we do on top of that I do have other thing, look how sad my cat is. So when you connect the dots in between, you could see a dog is walking past a field, a man is walking in the field. So these two sentences are being mapped together. Why? So when you see the meaning of the sentences, right, a dog is walking past a field, a man is walking in the field. So the field which we are having, the context, so they are both at a particular place, a field, right? So it's going to map those things together. And when you see the below sentence, there is a dog running past the field. Even you could understand previously we do have a dog running past in the field. So most of the things are being arranged similarly. So when you understand the architecture of how these embeddings are being made, so that's where you'll be more enthusiastic in these things. So once the embeddings are actually generated, right, so there are dedicated vector databases we'll be having. So we need to store these entire embeddings that have been produced onto particular vector databases. So these databases are actually optimized for high dimensional operations, and they usually use the nearest neighbor algorithms for having the understanding of all the data points, vector data points they are having. In the use case, if you see here, a dog is walking past a field, a man is walking in the field. So these two have some nearer meaning. So they'll be connecting in between. So when I've asked the LLM or the RAG system, what does a dog do? So it's going to give me most probably response, a dog is walking past a field. So this is how the semantic are maintained inside a vector databases. And now the next steps comes into the picture. So we are going to store these embeddings somewhere, right? So as I mentioned previously, if the embeddings are too small, consider a PDF of 2 pages. So we are going to get some limited amount of embeddings. So from that, we are going to store that in a PyTorch, tensors, or NumPy arrays. That could be enough for processing and giving us an output. But when the data is huge, so when I mention huge word, we are considering around 1 lakh PDFs, or it could contain even more than that. So at that point of time, we definitely need to pass on to the bigger vector databases like Pinecone, Quadrant. Any of those things could be useful for you. And finally, the idea comes into the retrieval and generation. So when a user provides something, it need to be converted into an similarity search and need to retrieve. If it requires some tools, it need to integrate those tools and accordingly have some ground research going on, need to give you some output. So this is the monolithic RAG architecture, I would say, that we are currently having. We do have some frameworks that implement the RAG systems, but Gemini File Search API made that even more easy. So we'll start with understanding the how does that Gemini File Search API is making these 5-step process into simple thing. So the File Search API actually collapsed these entire complex multi-stage pipelines into single fully managed tool. How? Instead of manually orchestrating everything, so we in each layer in the data ingestion we need to use PyPDF or PyMUDF, or in vector databases we need to consider whether to go with the tensors or whether to go with arrays or any vector databases like Pinecone or any other thing. Instead of maintaining all these things, right, Gemini File Search API have given us a simple way to use and get the file search things done. So we'll understand what is the actual difference between the Gemini File Search API as well as a traditional custom RAG architecture. So you could see here when we come to the core components, right? So the modular stack that we are having, the chunking, the ingestion, chunking, embeddings, everything, right, is being managed by the developer or the core architecture itself. But Gemini File Search API, it has been fully integrated with a single API call abstraction. We are going to get everything done, and I'll walk you through what does this single API call is going to do. And the ingestion process, there are different ingestion process. If you have images, we need to consider other thing. If you have tables, we need to go on with other things. But Gemini has made it even more easy with a single file. As I mentioned previously, with a single API, it made it even more easy. And chunking strategies, as I mentioned previously, there are different chunking strategies that you could go with, but Gemini has implemented that chunking strategy even more affordable. So when we see that embedding model, right, so this is what making some sense. So they are using their own embedding model, Gemini embedding 001 model, for 1 million tokens. It's actually costing us around $0.15. So when I mentioned 1 million input tokens, you could even consider how much those words are. So 1 million token would be coming around 7,50,000 words. So that could be around 400 plus pages at a single time, and the cost for analyzing all those things comes in around $0.15. So this is actually making some sense. So when compared to other plans we are having, other embedding models we are having, this actually makes some quite better thing. So sources indicate that this system, the Gemini File Search API, is actually using recursive chunking. So as I mentioned previously, when you need to maintain the context, when you need to maintain the size, the difference between the context, recursive chunking is going to be the best thing for you. And when we see the Gemini embedding model, there is one interesting thing of the Gemini embedding model 001. How does that make? It was the powerhouse, and it's an optimizable file search API which is able to have some semantic search too. So it was an state-of-the-art technology which has been declared by the massive text embedding benchmark. Massive text embedding benchmark is a performance measure which could be measuring the embedding models and different embedding tasks. Gemini embedding model has the state-of-the-art as of ranking at the top now, and it's actually supporting 100 plus languages. So this is where the entire embedding model shift takes place. So if you provide the PDF either in English, either in other format, it could be able to understand, because it's having the capability to understand 100 languages. And the model, the embedding model, actually uses Matroksha representation learning. So what does this mean? Usually when we do some embeddings, right, so when we perform some embeddings, there could be different sizes fixed by some models. As if you take an example of Gemini, it has a fixed size of 3072. As well as if you take any other model we are having, if you take a Qwen 3 embedding model, it has a size of 4096 of chunk size, right? But the Matroksha represent learning actually makes some difference there. Instead of taking a huge amount of chunk at a particular embedding, it's going to divide it. So like if we are having embeddings of different sizes, we'll be taking 128, 256, 768. So we are creating smaller embeddings but maintaining the fastest retrieval. So that's where the embedding 001 differs from, and we could see what are the different sizes of embeddings that are being produced here. If you want to go more through the representation learning, so here there is a research paper that I'll be dropping down below so that you could take a look at it. As we discussed the previously, the single chunking method may not be optimal for handling different type of inputs user may providing. So Gemini currently using a recursive chunking, so that could not be suitable for every situation we are having. The custom chunking configuration. So you could define what type of chunk you need. The recursive chunking itself, you could define how much amount of chunking you need to do on that particular PDF, so that it's not being analyzed kind of thing. So it could be analyzed at each and every aspect. Yeah, every model comes with limitations. Even to the Gemini, which we are discussing currently, having some limitations. You could see a blog written by the AI Automotors by the Daniel Walsh have written some important things on the limitations of Gemini API. So when you go all the way down, you could see here no markdown preservations and a basic chunking. Gemini does better embeddings and it could be able to understand. But when it comes to having labels there, the H1 and H2 labels are being missed in the particular document which is being provided, right? So what does happen if we are not taking any part of the PDF that was provided by the user? What could be happening? Obviously, the accuracy, the overall accuracy which we are able to get from a model or get from a rack system is going to be decreased. When accuracy decreases, definitely the system is going to be failed. So even Gemini is having some limitations that could be come up with different solutions. And vector storage, right, which we are having, Gemini is actually using the file search store. So this contains all the input that you have provided. So if a particular PDF has been provided to the file search store, that could be maintained until the 48 hours. So the 48 hours of time is there for you to maintain your documents. After 48 hours, it's going to delete the documentation from it. But the embeddings which have been made from the document are going to be stored entirely for rest of the life. Until you delete those embeddings, the file embeddings will be there in the file search store. So here is the simple use case that we could see here. So user will be providing an input to the model, and then if it requires some external knowledge, if it need to have some knowledge from outside, it's going to take that knowledge. Or else if it's required some document processing, it could generate a query, and the query need to be converted into an embeddings, so that embeddings will be passed on to the embedding model, and it's going to search in the database. So when I say database, we are going to a search of vector databases like Pinecone or whichever database we use. In the use case we are having, Gemini is using its own file search or database, so that it could retrieve more faster. So the user query will be passed on to the database, and then it could understand the context, it could retrieve from that documentation, it's going to give you the final answer. So this was a simple idea of Gemini File Search API, and we'll see the implementation of how does this File Search API is made. So you could get this file. I'll be building down the link below. So initially we'll be installing the Google GenAI kit. From that you need to configure your Gemini API key. So you could get your Gemini API key at the Gemini AI Studio. So as of now, we are using a simple poetry text which contains of the sample poetry, and we are passing on to the Gemini model to store it in a search store and then give us the analysis. So I'm going to upload the file to the search store. So it's saying that it has been completed the process, and then we are going to get that file, and we are going to pass on that file to the model that we are using. So as of now, you could use different models. So I'll give the collab file link in the description so that you could even use that. And we are going to just ask some questions. What does the text say about E Cummings? And then it's going to analyze that file and going to give you some response. So this is how the Gemini File Search API is making the complex RAG architecture. So when I say complex, you could see this is a simple RAG architecture without even having any framework. So while building these kind of architectures is going to take huge amount of time, and you need to have some more idea, or you need to be more developer oriented. So for the simple use cases, you could go with the simply idea of Gemini File Search API and build your own RAG systems. So I hope you got an idea on how does this Gemini File Search API is working on behind the hood. And if you find this video informational, uh, consider hitting that subscribe button, and we'll be coming on with more explanations soon. Thank you.